Good day. We've been spending a lot of time talking about units and dimensions. We've been doing a lot of calculations and so forth, dealing with how to convert one system of units to another and so forth. That's all pretty much mechanical types of things, tools that will be handy for you to be able to deal with quantities and units and dimensions. This is an important skill to have, but one of the reasons why dimensions and unit analysis are important is it can actually be a tool to help you probe some fundamental questions about the nature of matter and how it behaves and those kinds of things. And what I'd like to do in this module is to illustrate one way that you can do that, and that is to address a fundamental problem in the theory of gases, that is, where does pressure come from? Now, pressure is a quantity that is a property of gases. If you contain a volume of gas into a container, it's going to have some kind of pressure. And one of the fundamental problems in physics, in fact, a problem that was crucial to being able to derive the atomic theory of matter, was this property of gas pressure. Why do gases exert pressure? Where does it come from? And those sorts of things. Now, the basic theory that underlies our understanding of pressure is known as the kinetic theory of gases, and I will just outline that here. And the kinetic theory of gases says that the pressure actually comes from an interaction between the kinetic energy in a gas molecule and the walls of a container. So let's take the wall of a container right here. This is inside the container, and this is outside over here. And inside you have gas molecules that are floating around in there, and the gas molecules are flitting around. They're flying around inside the container, and in some instances those will collide with the wall of the container, and they'll bounce back. Okay, and the kinetic theory of gases says that basically the pressure comes from the momentum or the kinetic energy that is transferred from this atom colliding with the walls of the container. When it collides, it transfers its kinetic energy to the container and presses outward on it, and then that energy is eventually recovered to push the molecule back, going in the opposite direction. Okay, so the kinetic theory of gases, just to sum up, says that pressure comes from the interaction of kinetic energy of gas molecules with the walls of a container. If you take the molecule going at a certain velocity, then you can calculate energy quite easily with an equation, a standard equation, where the energy is equal to 1/2 times the mass of the molecule times the square of its velocity. This is a standard equation for calculating kinetic energy from the mass of a molecule. Now let's look at what the units of that calculation or that quantity are. We have kilograms, that's mass, times velocity, but we know that velocity has to be squared, and so we take kilograms. We know that velocity is meters per second to the -1. We square this, and we end up with units of kilograms meters squared per second to the -2. And we can reduce this to dimensions. We have mass, m, times length squared times time to the -2. Now, this is a dimension of energy. these are the dimensions of energy, you can calculate an energy quantity from any system of units that you care to. We happen to be using the SI system, where kilograms meters per second, but you could as easily substitute pounds mass for foot or inch times seconds to the minus 2 power. You would get a quantity of energy from that calculation, but it would be numerically different from the quantity that you get here. So this is one of the reasons why we're reducing this not only to its SI units, but also to its dimensions. So that's the kinetic energy side. But the kinetic theory of gases says that kinetic energy has to translate into pressure somehow. And let's spend a moment talking about what pressure is. Pressure is simply a force of something exerted over an area of an obstacle of some sort. In the SI system, the units of force are measured in quantities of newtons. A newton is defined as 1 kilogram meter per second squared. We can calculate force as force is equal to mass times acceleration, and this is where we get the units of kilograms meters per second squared. Now, what we are doing to calculate pressure is we are calculating a pressure over a unit of area. And so what we have here is we're looking at force times area to the minus 1 power. And the SI units for area are meters squared. And so pressure is going to be force times area to the minus 1. We know that this is meters squared. So our units of pressure are going to be kilograms, meters, seconds to the minus squared power, and we're going to multiply that times the SI units for area, which are meters to the minus 2 power. And what we will end up with there then is a derived unit of pressure known as the Pascal, which is kilograms, meters to the minus 1, meters to the 1, times meters to the minus 2 equals meters to the minus 1 times seconds to the minus 2. And our dimensions are going to be mass times length to the minus 1 power times time to the minus 2 power. All right, now we see the basic problem here. If you look at the dimensions of kinetic energy, mass times length to the squared, length squared, times time to the minus 2 power. That's for kinetic energy. But for pressure, our dimensions are mass times length to the minus 1 power times time to the minus 2 power. So there's a mismatch between the units, and it's a basic question to ask, how is it then that kinetic energy can actually translate into a pressure? The dimensions are entirely different, and well, they're not entirely different, but they're different enough to where we have a question that we have to answer. Okay, so let's go through and use a very simple analysis of units and dimensions to be able to explore this question. How is it that pressure derives from a kinetic energy? Now, let's pose one hypothesis to explain this. Molecules have kinetic energy expressed in dimensions of mass times length squared times time to the minus 2 power. But pressure is actually this energy spread out over a particular area, all right? And so perhaps our units of pressure can come from the division of kinetic energy over the surface area over which it's exerting its force. All right, now we can reject this on a couple of ways. First is with reference to common experience. All right. If the hypothesis is correct that pressure is simply energy spread over a surface area, one would expect then that a given volume of gas would have different pressures if they were contained in containers with different surface areas. And so, for example, let's take a cube. And each of those sides is going to be the same length, and that's going to have a certain volume. And let's take a sphere that has the same volume, but now the container that it is contained in has a different shape. You can do with a fairly simple series of calculations to show that the surface area of these two containers is going to be different. If you take the length of a side of this, cubes have length, height, width, and depth all of the same length, and you can say therefore that the surface area of this is simply L squared times the fact that you have 6 faces times 6. So that is the surface area of this cube right here. All right. It's a little bit more complicated for the sphere, but what you can do is you can show that the surface area of this quantity here is entirely different. In fact, the surface area is 4 times pi times the radius of this sphere squared. And if you do the calculations for a given volume, you'll see that the two have entirely different surface areas. And one would expect, therefore, that if the energy over surface area explanation was correct, that these two would have different pressures. In fact, you can demonstrate this fairly easily. The pressure is the same in both of those, and so that means that just on the basis of common experience, we can reject that hypothesis. But we can also reject it by reference to the dimensions as well. So, for example, let's take our hypothesis and state it in a word form. We're saying that the kinetic energy inherent in a gas over the surface area of a container is going to translate into pressure. Okay? Well, we can very easily come along and calculate what the dimensions of these things are going to be. We've already established that the energy is going to be kilograms times meters squared times seconds to the minus 2 power. And we know that surface area is going to have units of meters squared. These two are going to cancel, and what you'll end up with over here is units of the calculation of kilograms times seconds to the minus 2, kilograms per second squared. If we come back and look at our measurement of pressure, our dimensions of pressure, then we see that the units are different. For pressure, we've calculated from the first principle that pressure is force per unit area, that the units are associated with that are kilograms times meter to the minus 1 times seconds to the minus 2. So the units differ. So the units that derive from our hypothesis that energy is spread over a surface area gives us units of this, but the units do not agree. And when you're talking about translating one kind of property into another, one of the things that you're going to find is that the units must agree. And the disagreement between the units is enough of a proof that the energy over area hypothesis is incorrect. All right, so let's now take a different approach to it. Let's take an equation. Let's put in the pause here. Let's take a different approach to it. Let's take an equation that if you've had general chemistry, which you should have had in high school and which you probably have had here, one of the equations that is seared into your memory is the so-called ideal gas law. And let's put that up on the screen here. And the ideal gas law simply says that pressure times volume is equal to the molar quantity of gas molecules times the temperature measured in kelvins times a quantity R, which is known as the universal gas constant. Okay. Now let's come along and look at this equation in a bit more detail. Let's look at the left side over here. pressure times volume. Let's have a closer look at what that quantity looks like. All right, now we've already established that pressure has units of, dimensions of mass times length to the minus 1 times time to the minus 2. That's units of pressure right there. The dimensions of pressure, I beg your pardon. Volume, on the other hand, has dimensions of meters cubed, or length cubed. Okay? And so what we end up with here is a quantity that, when we calculated it out, has dimensions of mass times length squared times time to the minus 2 power. Now, that is the dimensions, you'll recall, that are energy. All right, so there's a clue. There's an important clue that we're kind of on the right track. The product of pressure times volume is equal to, or has dimensions equal to, the dimensions of energy. So the product of pressure times volume is energy. That's one side of it. Now let's turn to a better derivation of what pressure is. Let's take our ideal gas law. Pressure times volume is equal to molar quantity times the temperature times the gas constant. And now we want to isolate pressure on one side of the equation, so we'll take pressure, we'll divide both sides by volume. We're going to do a clever thing here. We're going to isolate molar quantity per volume, multiply that by the temperature and the gas constant. All right. Now we have pressure on one side, and we now have a new quantity over here, which is the concentration of gas molecules. That's what concentration is. Number of moles per meter cubed or liter or whatever volume or measurement of volume that you care to use. And so pressure then is going to equal concentration times temperature times the gas constant. Now, I've taken this equation to this point right here because we're going to run into this form of equation again and again when we talk about pressure, when we talk about osmotic pressure, and other kinds of quantities like that. So just keep that factoid in mind over there. But what I want to do here is to point to this equation right here. If this is energy on this side, then units and dimensions must agree. That means that the product of molar quantity times temperature times the gas constant also is energy. The units must agree. Now, what we are doing here is we are saying that now pressure on the left side of the equation is equal to energy, that's NTR, divided by volume. So we've gleaned a fundamental insight into what pressure is. Pressure is not the kinetic energy of molecules spread out over a particular surface area. What pressure is a kinetic energy of molecules spread out over a volume. So it's a measure of energy density more than it is of energy. And this reconciliation of pressure with one set of units with energy with another set of units points to this basic insight into what gases are and where pressure comes from. It doesn't come from kinetic energy of molecules spread out over an area. It comes from a kinetic energy of molecules spread out over a volume. Well, that's all for now, and we will come back to another set of discussions in another set of modules in this series. Good day.